Hi everyone, I'm Zhao, currently an assistant professor at Tsinghua University. It's unfortunate that today I cannot come to present in person, but still I hope my remote talk can make all of you inspiring. The title of my talk today is Scaling Autonomous Driving with Occupancy and Map Learning. Let's first take a look at a simplified version of self-driving technology stack. The perception module outputs dynamic object 3D bounding boxes, and the high-definition map module retrieves lanes and the traffic lights information based on high-precision localization. The 3D bounding boxes and high-definition map elements are then fed into the prediction module for trajectory prediction. And finally, our self-driving car plans its trajectory based on the observations and the forecasts. Last year, we have built a vision-based model following this pipeline called VIP3D. Here is a video demo of VIP3D. The surround view camera images shown above are the input of the model, and the animation below are the output of the system. This is an end-to-end model with intermediate supervision. I hope you like it. Okay, the video demo is a bit long. We'll skip the rest part of it. The video demo is cool, but is that the whole story? Today, we care about the scalability of autonomous driving technology. There are two questions. First, in the video demo, we only show pedestrians and vehicles, but many objects could appear on the road in the real world, especially in the dense urban areas. Are 3D boxes and trajectories enough to represent everything? The second question is about the high-definition map module. We definitely want our self-driving cars to travel around the world. However, these high-definition maps are all annotated manually by human beings. If we rely on human-annotated HD maps, how do we handle new geolocations? Let's first talk about the first question about perception. In self-driving, we use the term general objects or general obstacles to talk about long-tail distribution of things that we observe on the road. They include many different types of long-tail objects. For example, irregular and deformable objects, such as crane trucks, bendy buses, trailers, and etc. They are typically not rigid boxes like cars, but they usually have multiple parts. Say, a crane truck has a movable mechanical arm that protrudes from its main body. Then modeling it with a simple 3D bounding boxes, there will be two cores. We also have uncommon objects that stays out of the ontology tree. For example, the trash cans on the road or trashes scattered on the road. They are often unlabeled in the datasets. Finally, even for a known object with regular shape, a strange pose could also make it out of distribution in the point of view of machine learning. Say, an overturned truck. These general objects make 3D detectors having a very hard time recognizing and localizing them. That is why 3D occupancy becomes a desirable representation. The 3D occupancy was also advocated by Tesla last year. Now let's compare the 3D occupancy prediction task with other tasks in self-driving. Here in the plot, the horizontal axis is semantic expressiveness, and the vertical axis is geometric expressiveness. On the left, we have LiDAR occupancy grid mapping, which is a classical scene reconstruction task in robotics. However, it only works on static scenes and does not care about semantics. In the middle, we have 3D bounding box object detection, which is the most popular representation now. It performs okay on both metrics. On the bottom right, we have 2D image semantic segmentation and 3D point cloud segmentation. They are competitive in terms of semantics, but stays in a lower dimension or sparse representation in terms of geometry, like the point clouds. And finally, on the top right, we have 3D occupancy prediction, which offers us dense voxel predictions in the 3D world together with rich semantics. There are many recent efforts on occupancy prediction. This is a super hot topic right now, and there are many papers coming out every month. But we observe that there's a notable absence of high-quality datasets together with the benchmarks. Actually, constructing such a dataset is challenging due to several reasons. The first one is sparsity. As we know, the LiDAR point clouds are sparse, but the occupancy grid we are trying to build is dense. Second, occlusion. Since during the data collection, some parts of objects are not observed, and then how do we auto-label them? Or do we need to auto-label them? Third, 3D to 2D misalignment. During the occupancy labeling, there are disparities when we project the 3D voxels onto 2D images, which is often induced by sensor noises or pulse errors. How do we handle them? To overcome all these challenges, we create a semi-automatic label generation pipeline. The effectiveness of each step within our pipeline is rigorously validated. Let's go through the whole process. First, assuming we have a dataset with LiDAR and image sequences, like Waymo Open dataset and NewSync dataset. They are sparsely labeled point clouds and images because the frame rate is really high, so we only can select some frames to do the annotation, manual annotation. And in our pipeline, we first segregate the static scene and objects according to the 3D bounding box annotations. And then, for the static scene and each foreground object, we try to aggregate all the point clouds, including the unlabeled point clouds, according to the object trajectories and further refine with ICP. And after this, we obtain a denser point cloud. And then we assign semantic labels to the unlabeled points with KNN voting. And in this way, we obtain a dense point cloud with every point with semantic labels. After point densification, we found that still there are many holes on the object surfaces because some areas might not be scanned by the LiDAR points. Therefore, we perform mesh reconstruction to get smoother surfaces and remove the holes. And after we got meshes, to get the meshes for the scene and objects, we use VDB Fusion, and for the ground, we perform local plane fitting. And after we obtain these dense meshes, we do resampling so that we can get dense occupancy grid. But this is not the end of the story. We perform two additional steps. The first one is raycasting, which produces visibility masks so that we know exactly for each voxel whether it is observed by any sensor at the current frame and across time. They will be very useful later. Additionally, due to the pose drift and object deformations across time, the temporal aggregation of point clouds usually lead to the blurriness in a 3D space or the voxel leakage, as shown in this picture. So we take image semantic labels to further refine the object boundaries, also through raycasting. This is especially effective on thin objects like pose. And finally, we can obtain a dense 3D occupancy representation of a scene. And we list many design choices in our auto-labeling pipeline and show that each step makes sense and improves the final performance. Here is a visualization of the 3D to 2D consistency. We show the 2D image semantic labels and the 3D voxel auto labels projected onto 2D images. You can notice that all the details that we have preserved. Now let's talk about the visibility mask. It actually defines two kinds of tasks depending on our goal. If our goal is to truthfully reconstruct the observed scene, then this is a semantic occupancy prediction task, which is a pure perception task. On the other hand, if our goal is to infer the occluded region as well, it becomes a semantic scene completion task, which is regarded as A-model perception or reasoning. This A-model perception or reasoning is useful for downstream tasks like prediction and planning. Let's say we only see part of a car due to occlusion. We should still estimate its full scale for safe future interaction and navigation. So based on our auto-labeling pipeline, we introduce two benchmarks to you. The first one is OCC3D, a large-scale 3D occupancy prediction benchmark for autonomous driving. As we said, we not only label the common objects, but we label the general objects as well. This benchmark is built upon two existing datasets, the NewSyncs dataset and the Waymo dataset. And the second benchmark is called SSCBench, a large-scale 3D semantic scene completion benchmark for autonomous driving. Part of these datasets are already released. Please check them out through the QR code and our paper link. Okay, that's about scaling autonomous driving perception. And now let's move to the second question: how to handle new geolocations and how can we automate high-definition map construction? Classical methods of annotating and maintaining high-definition maps involves a really complex pipeline. As we know, we will have a survey vehicle driving around the city to collect point clouds, and then we will densify the point clouds with temporal aggregation and remove dynamic objects. And then we ask human annotators to mark the high-definition maps on top of the point clouds. And when we use it, we need to perform high-precision localization so that we can retrieve the high-definition map elements. It gives us really nice, precise maps. However, it is costly and labor-intensive. Moreover, the road conditions are ever-changing. To enable long-term use, high-definition maps demand constant updates and maintenance, which is almost impossible for manual annotation. So around 2 or 3 years ago, researchers proposed to make online mapping inference with the neural network. The neural network takes the camera images or LiDAR point clouds as input and outputs a local semantic map. In this way, we can turn a mapping problem into a perception problem. Online map inference is really nice because it's cheap and automatic, and it perceives the dynamic environment automatically, so we don't need to do map updates anymore. More concretely, at the beginning, we formulate the mapping problem as a segmentation problem. The high-level idea is that we first convert the perspective view images into the bird's eye view space, and then perform pixel-wise labeling on the bird's eye view space. And we'll label each BV pixel as lane markings, pedestrians, crossings, and etc. And after we have the semantic segmentation map in the bird's eye view space, we further perform some post-processing to obtain a final map. And we show the results on the right-hand side. More recently, we proposed to train a neural network that directly outputs the vectorized maps so that no more post-processing is needed. In our paper called VectorMapNet, we use polylines as the primitives to represent map elements. For example, a polyline can represent a lane, can represent a traffic sign or a pole stop sign or a pedestrian crossing. And then we pose the mapping problem as a detection problem. As we know, object detection is about detecting a bunch of boxes. Now, map detection is to detect a bunch of polylines. They are very similar, right? And so we design a detection transformer-like model to solve this map detection problem. Here we have some cool demos of VectorMapNet in time. As you can see, from the surround view camera videos, we can construct high-quality vector maps. Here's another example. But online map inference is far from perfect. It gives inferior performance compared to human annotations due to several issues. Say, the sensor field of view is limited due to occlusions and etc. So, can we do even better so that it performs very close to the human annotations? So I started thinking about how we human beings memorize the roads, and also inspired by a pioneering paper in neural memory, we proposed a memory network for high-definition maps. Our paper is called Neural Map Prior for Autonomous Driving. Here is the motivation. Driving in bad weather can be tough for self-driving cars. Due to the reflections on the road by the water, it's hard to infer accurate maps in real time on board. But imagine if these cars could remember how the road looked in a sunny day. In the same location, but in a sunny day. And then we can potentially recover the road structures, the maps better. That is what we have done with our system, Neural Map Prior. We take the sunny day observation and put it into a neural memory. It's like giving the car a memory of good weather and uses to improve the mapping when the weather turns bad. we have also developed a fusion module to blend the memory with what the car sees in real time. So our maps for raining conditions got a lot better after the fusion. Compared to traditional mapping that I have just talked about and the online map inference like HDMapNet or VectorMapNet, Neural Map Prior takes the best of both worlds. It leverages neural representations to build and update a global map prior, which in turn enhances the performance of map inference on board. Here's the overall architecture of the model. It contains 3 parts. First, the yellow part is a local inference module, which can be any online map model like HDMapNet, VectorMapNet. It has an encoder and decoder architecture structure. Then, a global map module in blue, which stores all the map priors in the form of patches or tiles. And third, a fusion module that selects the corresponding map tile from the global map, fills it with online observations with cross-attention, and finally, the features are decoded to get better results. These procedures are interconnected in a loop that grows stronger as more data is collected from vehicles navigating around the world daily. That is to say, we'll start from a 0 or blank neural map prior, and then as the vehicles drives across the city, and the map priors will automatically and gradually be built, and the online map inference performance will get better over time. According to our experiments, the neural map prior provides advantages such as extending the range of map perception, especially with improved performance in distant regions. The neural map prior also provides significant improvements in rainy and night driving conditions. And finally, here are some visualizations of neural map prior. Comparing the second column and the third column, we can see that with the neural map prior, our map perception results get more robust and of higher quality. Okay, finally, back to the story of scalability. We're also trying to scale the neural map prior technology to construct map priors for all the intersections in a city in a short period of time, because no labeling is required in this process. This is still in progress, and stay tuned. Okay, and finally, I would like to thank all my students and collaborators for their efforts and contributions to all these amazing projects. And my lab has multiple papers related to autonomous driving accepted at this CVPR. Check them out if you're interested. Okay, that's everything about my talk. I'm happy to take any questions.